Hello, everyone. Welcome back. Let's talk a little bit, once again. The intention of the next few films, the intention present, I guess you could say, is for me to make 3 films regarding review for electricity and magnetism, review for a final exam for electricity and magnetism. The review for the final exam for electricity and magnetism, those of you who have me as a teacher, you already have hard copies of what the review questions are. You have hard copies of what the review questions are. There's 72 review questions, and you have PDF solutions for every one of those 72 problems fully solved for you. Of all those 72 problems, I will take 36 of those 72 problems, half of them, and solve them on film. Whereas all the problems, however, the practice exam itself consisting of those 72 problems and all 72 solutions worked out for you, all of those will scroll at the end of the practice exam. There will be a total of 3 parts to the practice exam. I'm trying to shorten it up a little bit, where I cover the 36 problems I chose to cover. But at the end of every one of those practice exams, at the end of every part of the practice exam, the entire practice exam will scroll at the end of the film, each film, and all the solutions in PDF form. All 72 solutions will also scroll at the end of each of the 3 films. So the entire practice exam and all of the solutions will scroll at the end of each of the 3 parts of the review for the final exam. Even though I'm only doing half of the problems on film, 36 of them, all 72 problems fully solved will scroll at the end of each one of the 3 parts of the final exam. This right here, we're going to start after looking at all this. We're going to start with part 1. How many problems that is? Again, roughly for each part, we'll see what I'm intending to do. I'm making this first, and then I'm going to tack on the solutions afterwards. So this is going to be in the front end of what you're seeing. This is what you are going to be seeing. Roughly 12 problems for each of the 3 parts, giving you the 36 problems. Part 1 is what we're about to get into. Again, we're talking about electricity and magnetism, final exam review, parts 1, 2, 3. All 72 problems fully solved on PDF document and available to students at the end of each film. We just said that. 36 problems of the 72 problems will be solved on film, but the PDF for all 72 problems and their solutions will scroll at the end of each of the 3 films. Okay? So we know that. This is the introduction I wanted to give pertaining to part 1. I'll be doing the same thing for part 2 and 3. So I'm going to leave this up here, just give you some background, and then we'll have everything that we need. We'll roll through some of this, and this is extra practice for you. Many people will, or I don't know about many, but there are people who will tell you, and I'm among them, they would sometimes rather just have a good PDF document in front of them and go with that. Oftentimes, they'll just say, just give me a good PDF, I'll look at it, I don't need a film. It's easier if I just look at the PDF. So you've got both options, okay, for all 3 of these exams. You're going to have the entire PDF for all of that, okay? All right, we'll be starting up with part 1 at the appropriate time. You'll be seeing that real soon after this introduction that I just gave you. The same discussion or introduction would be happening for parts 1, 2, and 3, okay, as well. Okay, thank you. Hello, everyone. Let's do part 1 of what we were talking about regarding the electricity and magnetism final exam review. For part 1, let's start with some of the problems that we're doing. Problem number 1 in the electricity and magnetism final exam review. Problem 1. For problem 1, 2-point charges are 12 centimeters apart. They are moved to a new separation of 3 centimeters. By what factor does the resulting mutual force between them change? So, you can look at it a bunch of ways here. Let's take a look at it. Let's say number 1, let's do an F1 over F2. Now this is, a lot of times I'm basing this on all the material that we have covered up to this point. You have access to these formulas in one form or another, and we've derived many of these formulas, or at least we have verified that these formulas are true through experimentation, and or we've derived them somehow, or that, like I said, through empirical observations, we've verified some of these formulas, or through derivation. F1 over F2, let's say. Well, F1 regarding the electrostatic charges would be the constant K, Q, big Q, small q, it's like Q1, Q2, but here I'm just differentiating what the charges are in a different manner. This is R1 squared compared to KQ, Q, big Q, small q, over R2 squared. This is what we're talking about. At that point, there's a lot that goes on. Well, one thing's for sure. A fraction divided by another fraction is the first fraction multiplied by the reciprocal of the second fraction doing the dividing. Multiplied by the reciprocal of this second fraction doing the dividing, it flips downward. Make a long story short, all that cancels out. There's a 1 here, a 1 here, and the way everything flips, the R2 squared goes on top, the R1 squared is right here. A lot of ways you can do this. The ratio of squares is the square of the ratio. You can write it like that. Well, let's see what kind of things we're talking about here. Let's call R2 the 12, let's call R2 12 centimeters in this whole process. You just got to have some kind of consistency as to what's going on. R1 is going to be 3 centimeters. Centimeters is going to cancel out. What we're talking about is 12 over 3 quantity squared. 12 over 3 is 4. 12 over 3 is 4. 4 squared is 16. So by a factor of 16. In our situation, in what's handed out to you, and you'll see all of this, as we said, I sound like a broken record here, if I've not already sounded like a broken record. The electricity and magnetism final exam review the entirety of it, all 72 problems, will scroll at the end of each of the 3 parts of the films pertaining to that review for the electricity and magnetism final exam, the review for that. So all of that, all 72 problems are going to scroll. You'll see it here. Problem number 1 had the option of D that has 16, so there you go. That was D according to what I have on there. 2, let's go to problem 2. Charge A and charge B are 3 centimeters apart, and charge A is plus 1.44 coulombs, and charge B is plus 3.10 coulombs. Charge, again, guys, all of this, those of you who are in my class have access to this hard copy right in front of you. Everybody who's not in my class has it at the end of every one of these videos. Of all 3 of these videos, at the end of each of these, you will have all 72 problems scrolling for you. So you can always look at it. There are ways you can print that out as well. And you'll also have all 72 solutions solved in detail for you. We're just going to do 36 of them over these 3 films that we're doing. So all of it's going to be there. So I'm just reading it to you now, but you'll, one way or another, you're going to have access to all of this for all the films. Problem number 2. So as we said, charge A and charge B are 3 meters apart, rather. And charge A is plus 1.44 coulombs, and charge B is 3.10 coulombs. Charge C is located between them at a certain point, and the force on C is 0. So there's a net force of C there. There's a tug of war. It's an even pull on each side, and the net force on charge C is 0. How far from charge A is charge C? So let's take a look how we want to look at that. We will see FA on C, let's say here, and the way I got it written on there, FA on C, you can write it like that. We'll say that's FAC. The force A exerts on C, the force B exerts on C, and that's FBC. And we said it's a tug of war that ends up in a dead heat, ends up in a draw. They are 3 meters apart. So you've got a situation here. Let's do it. 3 meters. This is associated with A. This is associated with B. This is C. It's just a guide now, guys. I mean, we're right here. This distance right here is X. This distance must be 3 minus X, because X and 3 minus X will add up to 3. That's kind of the argument that you're making for this to happen. Charge Q sub C, we'll just call it Q. And there's a lot of ways we can go here. Let me just make sure I'm doing this right. Okay, let's try to follow some kind of order on this thing. If we're going to say this, we're going to say FAC equals FBC. Now, we already talked about that. We've already said that. It's got to be that way. How does this work? Well, it's going to be K times the A charge. And the units are all in agreement, so we don't have to write specifically particular units if all the units are proportional to one another, are in agreement with one another. C charge is Q. The distance between those two is right here. Okay, so one of them is, as we look at it, a bigger piece of chalk, guys. Okay, so we got this. We got the x's right here. We got the 3 minus x's right here. And this is the center of all the action, you guys. This is where the C is. Okay? So we've got this associated with the, and then what's the distance between them? It's x, we said, right? We said that distance is x. This other distance is 3 minus x. That one has got k, the 3.10 they're talking about, and there's the q. They're all associated that way. Q is kind of in the center of all the action, so it's going to end up in both expressions. K and K cancel. Q and Q cancel. And we end up getting 1.44 over x squared. We got 3.10 over the quantity 3 minus x squared. And that's a big thing. I mean, this essentially, arguably, I guess you could say, is the hardest part of the whole problem. You get down to here, you should be able to take it. You should be able to get there. Many ways to go. Now, quadratics, you have to be careful with them. Oftentimes, there's two, you know, if there's a square in there, there's going to be two solutions. There's a lot that can go on. But there's a lot you can say as well. You know that realistically, x has to be a positive number less than 3. 3 minus x has to be a positive number less than 3. Both of them got to be greater than 0. And both got to be less than 3. So there's ways you can get around this. Make a long story short, manipulate that, put all the variables in terms of a ratio, multiply by this quantity on each side, divide by this quantity on each side. This is kind of easier done than said. Over x squared Okay. We got it to here. If this is the case, why don't you square root both sides? Be careful, but yeah, let's just do that. Let's square root both sides. Square root this. See what the heck's going on here. Well, at the end of the day, you got this thing right here. This ratio square rooted is 1.46723. Okay, not bad. From here, old-fashioned algebra, just multiply by x on each side and solve that algebraic equation. Let's right. I mean, you tinker with this a little bit, you guys. You multiply by x on each side, you get it down to here. You get the quantity 3 minus x equals 1.46723 times x. You got it to here. Tinker with this a bit. Add a positive x on each side. 3 equals 2.46723 times x. Divide by 2.46723 on each side, and you're going to get the answer. So let me put it somewhere here, guys. And we end up getting the answer as 1.216 meters. 1.216 meters. That's roughly, I mean, they're all kind of approximations at this point. I don't know what we're calling an approximation and what we're not calling an approximation, but we get basically to here. We're looking pretty good. The 1.22 meters, that's C, according to the sheet that we're looking at. So, you know, the letter's not the big deal. Get the right answer here. That's kind of the real big thing going on here. Okay, that's 1 and 2. Okay, guys, go to 3. I mean, we got 1 and 2 done. Actually, let's not go to 3. I'm skipping ahead, right? I mean, so we did 1 and 2. We did 1 and 2. Let's go to 6 and 7. For problem number 6, let's have a look at it. Let's read it. For problem number 6, if a metallic wire of cross-sectional area 4.0 times 10 to the negative 6 square meters carries a current of 7 amps and has a mobile charge density of 4.24 times 10 to the 28 carriers every cubic meter, what is the average drift velocity of the mobile charge carriers? Charge value is 1.6 times 10 to the negative 19th coulombs. Let's take a look. So again, some of the formulas we look at to see where we're going, let's take it. For 6, from the work that we have done, from the work that we have seen in the textbook and that we've talked about in lecture, we know a number of things. We've got small n, q, v sub d, that's the drift velocity, and this is the cross-sectional area. Cross-sectional area drift velocity, which is what we're trying to find, charge per carrier, and the volume charge density per carriers. Well, it's a pretty easy move at this point, guys. I mean, to get v sub d, you divide by everything here in a product arrangement. In plain English, just NQA, divide by the product NQA on each side, and you're here. So you've got this. Again, the hardest move you make, that's it right there, guys, based on what we're doing. They plug in the numbers. Here's 7. Don't do the division until you multiply everything, and I mean everything. 4.24 times 10 to the 28. That's a lot. It's a big number. It's a big enough number. I initially didn't write it down correctly. So we got that. I don't need too many parentheses, I guess. I already have it parenthesed quite a bit. I got this. 1.6 times 10 to the negative 19. And 4 times 10 to the negative 6. The best advice I can give on this, guys, telling you to be careful with it when you're doing all this, is, okay, it doesn't look great, but you should be able to understand what I'm trying to say here. You got it to here and make the move, and you should be fine. Make sure, if you're not putting in units, that's okay as long as you know that all the units agree with one another that you're using. If not, you have to make them agree with one another. So as we do this, 2.58 times 10 to the negative 4 meters per second is the drift velocity that they're talking about. Absolutely. Again, the way they write exponential 10 to the negative 4, they write capital E and they put a negative 4 next to it, and that means 10 to the negative 4. So that's their language. That's the way you're going to see it on the final exam as well, most likely. Okay? 10 to the negative 4 is capital E. 10 to the negative 4 is capital E minus sign 4 meters per second. They got it written like this. They wrote it basically 2.6 E negative 4, and that they mean that. They mean that. That's kind of the language they're using when they do this kind of stuff, guys. That is D. The 2.58 rounds out to the 2.6. That's D. Okay. Not bad. That's 6. Let's go to 7. 7, there's a lot of similarities here sometimes, but some of the games get played differently, I guess. For problem number 7, a high voltage transmission line of diameter 2 centimeters and length 150 kilometers carries a steady current of 1,000 amps. If the conductor is copper with a free charge density of 8 times 10 to the 28 electrons per meters cubed, how long, that's small n, 8 times 10 to the 28th electrons per meters cubed, how long does it take one electron to travel the full length of the cable? The electron has a charge of 1.6 times 10 to the negative 19 coulombs. As far as magnitude, it's actually negative 1.6 times 10 to the negative 19. But that's not, we're looking at magnitude right now. Again, it's a game. It's a game we play again. So let's see what we have here, guys. Number 7, same game, right? Same game, same equation. Solve for V sub D as we have already done in the previous problem. You're talking about something like this. Sounds good to me. Let's find out what that is. Well, it goes beyond just finding the drift velocity, but let's find it. The amps are something incredible. 1,000 amps. The amount of current is something incredible. The N is 8 times 10 to the 28. The charge, the sign's not really important at this point. We're trying to find, magnitude of velocity and get an idea how long it takes to traverse the distance. The cross-sectional area is pi r squared. If it is, just make sure here. For some reason, I want to make sure I'm reading this right. Right. The diameter of the, got to be careful, guys. Got to be really careful. The diameter is 2 centimeters. If the diameter is 2 centimeters, 1 centimeter is the radius. 1 centimeter is this. Again, you just got to watch it. Careless mistakes are easy to make. So we got this. Well, okay. I mean, wheel and deal with this thing a little bit, guys, and we got what it takes to get it done. V sub d is going to be, to what extent you take this. You want to just get, to be careful, I guess you take it pretty far. Now, if you're just doing stuff on a calculator, you can leave it on the calculator. I'm explicitly writing many things that you don't need to explicitly write when you're doing it on your own. Sometimes it helps anyway, but V sub d is 2.486 times 10 to the negative 4 meters per second. We need to know this. The distance x is covered in a time t. Here's V sub d, multiply by a time t, and you get that distance. Well, okay, that's a pretty easy move. To find the time it takes to traverse the whole distance, why don't you divide by V sub d on each side? Let's speak their language. 150 kilometers, let's go MKS system. 150 kilometers is 150,000 meters. This right here is 2.48, almost 2.5, 2.4868 times 10 to the negative 4 meters per second. Notice how you need things to cancel out. You got to have the right units going on. This is about 2.5. This is 10 to the negative 4. 2.5 goes into here. It's a good point. Let's just pretend it's 2.5. If it's 2.5 and it goes into here, it goes in about 60 times. Then this 10 to the negative 4 comes on top. It's 60 times 10 to the positive 4. 6.0 times 10 to the 5 seconds. Something like that. Or is it? For some reason, I'm not agreeing with this number already. Oh, yes, I am agreeing with this number. I'm not agreeing with what I did. The key is right. Maybe I should trust my earlier work, guys. Let's try this one more time. There's a little trick to this, which I did wrong. Hopefully I can do it right this time. This is about 2.5. 2.5 goes into 150 60 times. 60 times 1,000 is 60,000. That's 6 times 10 to the 4. Divided by 10 to the negative 4 makes it 6 times 10 to the 8. Correct. A little more, so that's about where it's going. That's kind of their round off. 6.0, 6 times 10 to the 8 seconds. Yeah, there were other. The number I'd actually gotten when we grind that out is 603,185,789.5 seconds. All right, 600 million is close enough given what they're asking us here. You got to look at what they're asking you. And if they're asking you something that's not really convoluted, just go with the non-convoluted answer. 6 times 10 to the 8th is found in the option D. So D is your answer for this one. So that's number 7, you guys. Not bad. Let's keep going. Again, I'm skipping around a little bit. Like I said, I'm not, all 72 are available to you, both if you're in my class, and we'll do it in class in other circumstances, and if you're not in my class, it's on here on the video. Everything is there, fully solved. And there are ways that can be accessed quite easily. You look at it at the end, how it scrolls. There are ways you can print that out as well if you want. That's up to you. The big thing is, let's get some good practice out of this whole process, no matter how we go about doing this. Let's go to 9 and 10, you guys. Take it from there. Okay, guys, 9 and 10. Let's take a look at number 9. A 1,000 volt battery, a 3,000 ohm resistor, and a 0.5 microfarad capacitor are connected in series with a switch. The time constant for such a circuit, designated by the Greek letter tau, is defined as the time that the capacitor takes to charge to 63% of its capacity after the switch is closed. What is the current in the circuit at a time interval of tau seconds after the switch has been closed? Okay, guys, also another great question, obviously. Again, a 1,000 volt battery, a 3,000 ohm resistor, and a 0.5 microfarad capacitor are all connected in series with a switch. The time constant for such a circuit, designated by the Greek letter tau, is defined as the time that the capacitor takes to charge to 63% of its capacity after the switch is closed. What is the current in the circuit at a time interval of tau seconds after the switch has been closed? Obviously, in these circumstances, the greatest amount of current flow, instantaneously speaking, is early on, before the capacitor has got a chance to get charged. It's going to freely flow. The more time we take, the less rate of current flow is going on. The less rate of charge flow, called current. The instantaneous current is the greatest at the earliest part and the least at the latest part. So somewhere in between there, after tau seconds, what are we looking at? So there's number 9, you guys. Basically, they're saying here, we've been down this road for charging a capacitor. You're talking about little q being the amount of charge that's on there. Big Q is the maximum charge that would be on the capacitor. And this is the way that all plays out. If you have T being a very, very big number, close to infinity, if that's not big enough for you, we make it bigger. But if it's very, very big, this part right here, not the 1, just this part goes towards 0. And then you get the maximum charge on there. Well, if they're telling you that tau is RC based on derivations that we have done at other points, it's not our job at this point to reteach the class, guys. We've already seen the material in one form or another. Whether we believe it or are comfortable with it or not, we know certain formulas, are allowed to use and will use certain formulas, right? We know this is the reality that we're dealing with. If you take, well, there's a lot going on here. If you're in a non-calculus setting, I'm just going to give you an equation here. If you're in a calculus setting, I'm going to take the time derivative of little q. dq dt will give me I. So in either circumstance, you're going to get this answer. This pertains to the time derivative of q, if you have some calculus background. For those of you that do have a calculus background, you know that, depending upon how I'm going to use this particular test, you guys. So, or how you would design a test on this. Let's find what I is. That's dq dt. If you're not comfortable with that, you don't need to be. Know that this is what is going on. Q divided by R is forgive me. Let's try that again. Q divided by C. Well, C is Q over electromotive force, voltage, or delta V or E. Q over E, This is Q over E. This is Q. Q divided by Q over E. The E goes on top. And after all that mumbo jumbo, we get to here. Sounds good to me. You get up here. Yeah, we can write it down there again. I guess I have it that way in the notes. This would be the maximum amount of current, guys, for the total E that's associated with it. So it's I max, that's E over R. This is E to the negative T over RC. Okay, been there, done that. There's a lot we can do. For some reason here, let me try to think about this. Now for this, yeah, right, exactly. I'm sorry about that. This is 1,000. This is 1,000. This is 3,000. This is interesting. This is interesting. This RC right here is tau. After, and when t is equal to tau, and RC already is tau, we're talking about, well, tau over tau is 1. You end up getting, you get a lot of stuff here. I mean, you get 1,000 over 3,000 is 1/3. This is -1. And the rest is, you know, basically you've got a calculator, go for it. You got 0.1226 amps. And what's that associated with? That was number 9, right? Correct. They got 0.12 amps. They didn't, you know, they're not going as far as we're going, and that's fine. Which one's the best answer? 0.12 amps for C. Again, this ain't a big deal. Just get the answer and then hunt around and find what you're supposed to find. The big thing is procedure. Can you get to what you're getting? Can you do what you got to do to get to there? A series RC circuit has a time constant of 1.0 seconds. That's tau. That's tau equals RC. The battery has a voltage of 50 volts, and the maximum current just after closing the switch, right in the beginning, is 500 milliamps. That is 500 over 1,000 amps. That's 0.5 amps. The capacitor is initially uncharged. What is the charge on the capacitor 2 seconds after the switch is closed? Well, if the time constant is 1 second, 2 seconds is 2 time constants. So that's of interest in its own right. Let's take a look at it. So for this one, we know that. You're charging a capacitor. Well, we've been down this road before. The time derivative of Q is the current. For a calc-based class, that's what you're looking at. Take the time derivative of this function. Take the time derivative of this function on each side, and you get I. Take the time derivative of this function and get what you're going to get. Well, the time derivative of that function is I. For those taking this non-calc, that's fine too. We've got RC e to the negative. Now, again, guys, this should look very familiar. Q divided by C, we said was that E thing. The potential difference, maximum potential difference. This is Q divided by E. The Q's cancel, the E flips up, and we get to here. E over R is the maximum current, so we already know a lot. This is the maximum current. I is equal to I max e to the negative t over RC. Now, let's deal with it. They're basically playing the game, you guys. There's a lot of games I guess we could play here at this point. Let's figure out, see exactly how I want to do this. I mean, there's a number of ways we can do it. I'm following pretty closely what the notes are here. You don't necessarily have to. The big thing is, in the end, the notes are all going to agree with one another, and we should be okay. Well, the question is, how much charge on the capacitor at that point? So there's a lot to say. We will say, the way this is going to play out here, I guess you could say, they told us that I max was 500 milliamps. That's 0.5 amps. Let's make everything agree with the MKS system of units. So we got that. We're leaving this up here because it's going to get us to a lot of things, but there's still more things we have to do, quite a few. They're telling us that tau is one, so they're saying a bunch of things here, I guess. They're saying that tau is 1 second. They're telling us that tau is 1 second. E is 50 volts. We know quite a number of ways we can actually go here to do this. Number of ways you can argue this, guys. You can come back, because in the end, okay, there's nothing which is not valid here. There's nothing which is not valid here, but what's the best use of the data that we have? Perhaps it's coming back here. We're trying to find what kind of charge is going to be on the capacitor. This is just telling us, well, this is all useful, interesting. The time derivative of the charge, the time derivative of the charge function, easy for me to say, is the current. Okay, we know that. They're not really asking us for that, though. They're asking us how much charge is going to be on then. The big Q is the max. Is there a way we can kind of figure out what's going on here? Well, we could say this. We could say we know that. We can come back here. We can say that I max was all this business right here. Well, I don't need to go this far. I want to keep the Q alive because I want the answer to have a Q in it. Q is what I'm trying to find. Everything here I've done is valid. All of it's valid. But since we're looking for Q, maybe all of this being valid, let's come back to this stuff. Let's come back to this and see what we can say. Let's come back to this and these two things. These play a big role about what's going to happen here. Well, RC, that's interesting. I mean, I max is Q max over RC. I max RC is tau, and they gave us that. So Q is tau times I max. That's pretty interesting. That's pretty interesting to play that. Well, Q is tau times I max. Well, okay. They told us I max, that's the big Q. They told us tau was 1 second. I max, they told us, was 50 volts. If we play the MK, notice I didn't put any units here. I know the units are going to be agreeing with me because I'm using volts, coulombs, not millivolts. I'm using just regular volts. I'm using seconds. I'm using volts. So it's going to be okay. At the end of the day, you're getting, let's see here. That was the voltage, rather. I'm sorry. That 50 is not true. That 50 would be in regard to voltage. In regard to I max, it's 0.5 amps. Okay. Q is 0.5 coulombs. So you're looking at a situation where you've got Q, little q right here, is big Q, 1 minus, and maybe that's where we got to stay because we're dealing with charges. Again, this is the kind of stuff you don't need to lecture running across 30 feet of a room. You just got to make sense for yourself when you're doing the actual problems here. They said big Q, which is Q max, is going to be tau times I max. Yeah, we just said that. We said that earlier. Yeah, we said that. Now, tau times I max, we found to be 0.5. It's a bit convoluted, but we did it. We found it to be 0.5. This right here is 1. The E is E. RC is tau on the bottom. And after 2 of those time constants, we got 2 tau. Well, 2 tau divided by tau is 2. After 2 time constants, 2 tau divided by tau is, forgive me, that should be a negative right here. So it's negative right here, negative right here. 2 tau divided by tau is 2, so there's a negative 2 right here. You grind this thing out. .323 coulombs. Okay. That's that. Sure is. 0.4323 coulombs. Let's see where that's at. 0.43 coulombs here, they got A. So obviously you know this, guys. I mean, you look at it, you'll see where it matches up. For those of you who are going to watch this and only have it when it's scrolling, you can look at all these and see where everything scrolls to, and you see where all the solutions are. These are the solutions. Both the final exam review for electricity and magnetism, the questions, that actual exam review is going to be there, and the answers to that exam review, all 72 problems, as we've said countless times by now. So you're going to see all that. That is the situation there, guys. That is 9 and 10. That is 9 and 10. All right. Let's look at 11, 12, 13 and see what's going on here regarding that. All right, let's see what we got here, guys. Let's look at number 11. Number 11, a series RC circuit has a time constant. For number 11, a series RC circuit has a time constant of 0.900 seconds. The battery has an EMF of 24.0 volts, and the maximum current in the circuit is 0.5 milliamps, which is 0.5 times 10 to the negative 3 regular amps. Again, make everything agree with the MKS system of units. It's a real good way to go. That's number 11. They're asking, Or at least that's part of the introduction to it. What do they mean by that? Well, for number 11, after all that, they're asking, given those circumstances, what is the charge stored in the capacitor 2 seconds after the switch is closed? For number 12, they're asking you, what is the capacitance of that capacitor in which the stuff is being stored? So 2 different places there. There's a lot being said, I guess you could say. Q, when they put it there, means Q max. We've gone there. We've talked about that already. Q equals CV, pertaining to the formulas that we know. If V is that epsilon or E that we talk about, that I've been talking about, if the V is the same as that E, we go CE like that. They're telling us that tau is 0.900 seconds. Well, we'll just say 0.9. How's that? Tau is also equal to RC. Charging a capacitor, this is the situation in charging a capacitor. We feel pretty good about that. I mean, we've seen it in one place or another, and we feel pretty good about it. So we've got it to here. And there's a lot to be said here, I guess you could say. We can say, let's just throw some stuff in here and feel pretty good about this, I guess. We've already talked about some stuff. I mean, Imax, based on the stuff we've done earlier, we know it's coming out to here. And that itself is of interest because the E that we're talking about, the E is 24 volts. So let's see here. For some reason, I'm not agreeing with some of this stuff, but let me get a good view here. What's going on here? Yeah. Okay. Yes. This is fine. Imax is E over R. It's 0.5 milliamps. 0.5 milliamps is 0.5 times 10 to the negative 3 amps. If you play the game here, guys, and solve for R, multiply by R on each side and divide by Imax. We've got an interesting situation here. You can say, okay, I got this. What happens? It's a lot here. Let me try to kind of put it in some language that's going to make some sense to us. We can look at this. So we got that. That's true. Let's multiply by C on each side, and we got that. So we got, that's important. I mean, we've got RC equals CE over Imax. RC is tau. RC is tau. C times E is Q max. Is Q or Q, big Q or same as Q max. And the I max is on the bottom. Yes, true. So we solve for Q, big Q. Big Q is tau times I max. Sounds good to me. Well, what do we have earlier, guys? We had little q equals big Q times 1 minus e to the negative t over tau. Yeah, true. The big Q is this. So rather than write, in place of big Q, put tau times I max. It's a Fascinating run at it, guys, I can tell you that. They're saying at the end of 2 seconds what happens. The tau is 0.9. Let's just remember that. They're telling us the time constant, tau, is equal to 0.9. Tau is 0.9. 5 times 10 to the 0.5 times 10 to the negative 3 is this. You got this. Again, luckily we have calculators, right? And we got 4.0123 times 10 to the negative 4. 4.0123 times 10 to the negative 4 coulombs. Make this 100 times smaller, make that 100 times bigger, and you got 401.23 times 10 to the negative 6 coulombs. That is 401.23 microcoulombs. Yeah, sounds good to me. Q is 401.23 microcoulombs. They wanted the answer in microcoulombs, so we dance in that manner, I guess. We dance to that song. They're telling us microcoulombs for a final answer. We got to give it in microcoulombs. Okay, unfortunately here in the printing of it, guys, I got BCD here. I got BCD, but I don't have A. A had the right answer. A was 401 probably, 401 microcoulombs. So that would have been A. It doesn't show it here because it's just BCD, but that's fine. We know the procedure. We know the process. We get the answer. So there it is. That's what's going on there regarding this. So this was, at the very least, let me put down what problem that was, guys. Forgive me, my fault again. There's 11. And we got that. Now what are they saying here, guys? They're saying, give me the capacitance. What is the capacitance? Well, okay, let's just remember a few things, and we shouldn't be too bad off. We did 11. There's your answer for 11. Let's talk about 12. Give me the capacitance. You remember that Q was tau times I max in that circumstance. We also, that's the maximum Q. Big Q is the maximum Q. We also know Q is C times E. Well, wait a minute, it's two things here. Q, set these Q equal to each other. Correct? Set these Q equal to each other, and we've got this. Well, I want to find the capacitance. Sure. We'll solve that then. We got tau times I max. We got tau. We have tau times I max divided by E. Yeah, pretty straightforward stuff, guys. Tau we said was 0.9. We were talking about that earlier. The I max was 0.5 times 10 to the negative 3 because it was 0.5 milliamps, which is 0.5 times 10 to the negative 3 amps. And the E that we were talking about was 24 volts. The rest is what we need to do. You get 1.8. 1.875 times 10 to the negative 5 farads. That is, make it bigger here by a factor of 10, so you make the other stuff smaller by a factor of 10. That's microfarads. So we got C. C is equal to 18.75 microfarads. For number 12, yeah, they got 18.8 microfarads. The 18.75, they rounded it to 8. The 18.75, they rounded it to 18.8 microfarads. That's fine. The big thing is, look at the answers, guys. It's pretty obvious that the best answer is what you got looking at you. That's 18.8 microfarads. That's C. And that was number 12. That was 11 and 12. Let's go to 13. Problem number 13. A high voltage power line 23.0 meters above the ground carries a current of 2,200 amps. What is the magnetic field due to the current directly underneath the power line? Directly underneath the power line, hitting the ground. I mean, I wish I would have said this a little more specifically, but directly underneath the power line, and probably right down to the 23. So let's see how that works out. That's basically what happened here, guys. So again, we know a lot of these formulas, folks. We've seen them, we've derived them and or seen them talked about as being indicative of the empirical phenomenon that we see in nature, and the mathematics describes that empirical phenomenon. So it's either it's empirically verified, or it could perhaps, some things can be verified mathematically, others are empirically verified, and from there they try to make the mathematics work for what's empirically verified, like Biot-Savart law or something of that nature. Well, we have what we have. All right, guys, so pretty basic stuff. The high voltage power line is 23 meters above the ground, and it carries a current of 2,200 amps. What is the magnetic field due to the current directly underneath the power line all the way down there? So, again, things can either be empirically verified and or mathematically derived and then empirically verified. The amount of B field, understandably, there's a constant, is directly proportional to the current and inversely proportional to the distance away from that current, in a sense. 2 pi is a constant, mu 0 is a constant. R is the distance away from that current, that's the amount of current. If you're far away from it, far away from it means inverse relationship. Far away from it, smaller B field. A strong I means very big B field. Big B field with a strong I, small B field with a large R. That is the setup. That'll give you the answer. It's as simple as that. Mu, they told us, again, just make sure the units, this is all based on MKS system of units. Use the MKS system of units and you're going to be fine. You grind that out. (19.13) times 10 to the negative 6 Tesla. That's 19.13 microtesla. Sounds good to me. Where's that coming from? Well, you know, what are they calling that? Well, you know, we said 19.13 is about 19.1. 19.1 microtesla, that's A. All right. Let's go to the next one. Let's look at 14. 14. Now there's a little different dynamic here, guys. For number 14, two long parallel wires. Two long parallel wires, 45.6 centimeters apart, are carrying currents of 13.0 amps and 23.0 amps in the same direction. Let's just say 13 amps and 23 amps. They're both, you know, two long wires are 45.6 centimeters apart. That's 0.456 meters apart. We want to use the metric system, MKS metric. This is all metric, but we're going to use the MKS with meters in there. Two long parallel wires, 45.6 centimeters apart, are carrying currents of 13 amps and 23 amps in the same direction. What is the magnitude of the magnetic force halfway between the wires? They're not really asking us beyond that. You know, what is the magnitude? What is the magnitude of the magnetic force halfway between the wires? Well, we're going to say that the two B fields aren't going to have a cancellation type effect on one another because they're going in the same direction, and so they're kind of aiding each other. If one's coming out this way, this is what's going on downward. Let's say it's positive current coming out this way, positive charges flowing this way. It's doing this. With the other one, let's see, they're coming in the same direction. Oh, you're going to do a vector sum on that, so it's not going to. They are going to cancel each other out actually. Let's take a look. This is a little bit easier done than said, so let's go there. Don't have a lot of time when you're doing some of these exams, guys. So you want to fly. They should be short answer, and they are. They force you to think a little bit, so you got to go in there having trained yourself a bit. But I'm going to do a vector sum between the two B fields and get a resultant vector associated with that. What is the distance between them? Well, we got 45.6 between them. Halfway between them is this. That's going to come out to, it's a good question here. What am I doing here? Let's see, 22.5, 22.8, I guess. 22 point, let me see here. Yeah, 22.5, and then half of that, okay. Yeah, 22.8 centimeters. Yeah, that was right the first time. I should have trusted myself. 22.8 centimeters is halfway between them. Well, yeah, good. Let's start talking the language of the MKS system. 22.8 centimeters is 0.228 meters. That's R. So we got it looking. We got that. We know a number of things. Generally speaking, for either one of the wires, this mathematical reality holds for either one of the wires. Okay. So what? Well, you're going to use it for each wire separately and do a vector sum. They do tend to cancel each other out. If one's coming out this way and it's coming down, the other one's coming out this way and it's going like this, but it hooks around, they both clash. So it's going to be a vector sum, and it's going to be smaller than what it was if they were going in opposite directions. Something to keep in mind. If the currents were going in opposite direction, the B fields would add up in a strictly positive manner, so to speak, or strictly negative manner. Here it's one's positive, one's negative, I guess you could say. Well, if that's the case, let's do the whole vector sum. The whole vector sum, B, in terms of a magnitude, is going to be mu 0 I over 2 pi r, and the other one's going to be mu 0, forgive me, It's going to be mu 0 I1 over 2 pi r. The other one's going to be mu 0 I2 over 2 pi r, and they tend to cancel each other out. Well, let's just talk about the bigger one kind of getting the upper hand here. And let's just have mu 0 over 2 pi r, and then put, let's say, I sub 2. I don't know if they actually put symbols here on it. They didn't really. So I'll call the 23, I'll call the 23 one. Let's just see here, guys. I want to make sure we're doing it right here. It's a little. That's the I2, and then here's the I1. We said the way it happens, like I said, it comes out this way, and this happens. The other one comes out this way, the same thing happens, but it hooks around and collides with the other one, so they're going to cancel each other out to some degree, not entirely, of course. So we do this, we play the game, and let's see what it says here, guys. Let me. Just looking for some chalk, guys. I swear I start out with a lot of chalk, and the chalk goes. So we got what we have here, guys. You play the game here. Mu 0 is the 4 pi. Four pi times 10 to the negative 7. 2 is 2, pi is pi, okay. They're straight out constant numbers. Here's 2, here's pi. Well, here's 2 pi, and here's 4 pi. 4 pi divided by 2 pi is 2. Kind of neat. Constant numbers all over the place, guys. This is 0.228. We talked about that in terms of the radius. And this right here, you got 23 minus 13. You go for it, and you got 8.777 times 10 to the negative 6 Teslas. B is 8.772. And there it is, guys. B is going to be, and again, the 10 to the negative 6, the 10 to the negative 6 is micro. So it's 10 to the negative 6 Teslas is microteslas we're talking about. 8.772 microteslas. Well, let's see what we got here, guys. Right. 8.772 microteslas is sure very close to 8.77. 8.772 microteslas is very close to 8.77 e to the negative 6 Tesla. So that's A. All right, guys, that's 13 and 14. Forgive me. That is right. Let me see. That was 13 and 14. Let me just see here. Right. That was 13 and 14. Let's go to 16. A planar loop consisting of 7 turns of wire. A planar loop consisting of 7 turns of wire, each loop encloses 200 square centimeters.
is oriented perpendicularly to a magnetic field that increases uniformly in magnitude from 14 times 10 to the negative 3 Teslas to 38 times 10 to the negative 3 Teslas in a time of 8 times 10 to the negative 3 seconds. What is the resulting induced current in the coil if the resistance of the coil is 5 ohms? Okay, there's a lot there, but I think once you get the setup, the rest should go pretty smoothly, guys. Shouldn't go too badly for us. So let's take a look at it.
Let me see what I can do, guys. I might as well just start it out here. Maybe erase a little bit when it's time to erase.
So again, it's a great problem. A planar loop consisting of 7 turns of wire. Each of the turns, my friends, each one of the turns encloses 200 square centimeters, is oriented perpendicularly to a magnetic field. The magnetic field hits the planar loop in a perpendicular fashion that increases, is oriented perpendicularly to a magnetic field that increases uniformly in magnitude. The magnitude of the magnetic field starts at 14 times 10 to the negative 3 Teslas and goes to 38 times 10 to the negative 3 Teslas in a time of 8 times 10 to the negative 3 seconds. What is the resulting induced current in the coil if the resistance of the coil is 5 ohms? Okay, there's a lot there, but it's not as bad as you think. You do have to be careful, though. Let me put the horse in front of the carriage here, guys. I just might as well get rid of this. Start over there a little bit, and we'll take it from there. I'll start over here, guys, and probably just work my way back the other way and see what I can say. Okay, so let's see a couple things, guys. Let's talk about a couple things. We know from some pretty basic mathematics, still pretty fascinating, 1 square centimeter is 1 centimeter by 1 centimeter. That's the same as 10 to the negative 2 meters by 10 to the negative 2 meters, which is 1 times 10 to the negative 4 meters squared. So 200 square meters is actually 200 times 10 to the negative 4 square meters. True. That's true. We've got that. We know that I, as a general rule, is E divided by R. The E, in terms of, don't worry about positive or negative, that's not a big deal. We're looking for a magnitude here, is the number of turns times the time derivative of the flux, or if we're not going to use a time derivative, we can use delta F over delta T, which is roughly equivalent to the time derivative of the flux, at least for our purposes. The negative is there because it opposes a change in the flux. That's okay. The absolute value is going to give us positive answers. This right here is potential difference at the end of the day. And this right here is R. Potential difference divided by R is going to give us the I that we're talking about here. If you plug in these numbers, it should go pretty good for us. Let me just go over here. Going kind of a little bit backwards here, guys, but that's all right. We're going to just walk our way around there. Let's see what we got here. I is E over R. We know that there's 7 turns. The negative's there, the negative's there. 38 minus 14 is what it is, times 10 to the negative 3. Little shortcut there. And then 200 times 10 to the negative 4. Okay, here. 200 times 10 to the negative 4. Okay. This all took place This all took place in a time span of 8 times 10 to the negative 3 seconds. The R is basically, I think it said it was 5 ohms. I don't know how I didn't write it there. Later on I wrote it there. This whole song and dance, you guys, this up here, this whole mess way up here is about 0.42, or maybe exactly 0.42. All of this up here is 0.42. This is 5, so it's 0.42 divided by 5. So I is equal to 0.42 divided by 5. Well, if it was 42, it would be 8.4. But it's not. It's 100 times smaller than that. So it's 8.4 times 10 to the negative 2 amps. Make that smaller by a factor of 10. You got to make this guy bigger. You got this. I'm already looking. They're giving the answer in terms of milliamps. So that's why I went here. 84 milliamps. That's what I is. Right? So we're looking okay. 84 milliamps. I knew it was milliamps. I mean, we looked at it and say, how they get, well, actually, they didn't go that way, which is okay. Either way, we're going to get it. Let's talk about 16. What are you getting? Well, they got here, the closest thing I got here, guys, is 8.4 E negative 2 amps. So I already told you that's 8.4 times 10 to the negative 2 amps. That's 8 right here. That's 8.4 E negative 2. That's how they wrote it. Well, what is that? That's this right here. Well, which one does that correspond to then? And again, that's not the biggest deal in the world, guys, but we got 8.4 e to the negative 2 amps, that's D. 8.4 e to the negative 2 amps, that's D. Okay. The big thing is this. Can you get it down to here? That is that's 8.4 times 10 to the negative 2 amps. It means the same thing as that in the language of the test. So make sure you're able to speak that language. Comes out to here as well. They didn't go that way, but if they did, we could go that way as well. Okay? That was number 16. That was number 16, you guys. Let's go to number 17. Number 17. What is the minimum frequency with which a 300-turn flat coil of cross-sectional area, that's a lot of turns, you guys. Let's go back to that. What is the minimum frequency with which a 300-turn flat coil of cross-sectional area, 370 square centimeters, the cross-sectional area, you guys, is 370 square centimeters. That's per turn. Can be rotated. What is the minimum frequency with which a 300-turn flat coil of cross-sectional area, 370 square centimeters, can be turned? Can be rotated. Okay? So what is the minimum frequency with which a 300-turn flat coil of cross-sectional area, 370 square centimeters, can be rotated in a uniform 25 millitesla magnetic field if the maximum value of the induced EMF is to equal 8.6 volts? They're telling us a lot, and there's a few things they're not telling us. They're not telling us the frequency. So we got to figure that one out for 17. All right, so with that one, it should be pretty straightforward, guys. Let's go for it. Let's see where we are when that does happen. They're telling us a number of things, and And we're going to play the game with the MKS system of units. There are 300 turns. Capital N is 300. The area is area for each one of the turns. Area associated with each one of the turns. There's 300 of them. Area associated with each one of the turns is 370 square centimeters. That's 370, and a square centimeter is 10 to the negative 4 meters squared. So we got that. The B field, B, is 25 millitesla. Milli is 10 to the negative 3. Emax, we want the Emax generated at the end of all this. What is the max going to be in this circumstance? Give me the frequency that's going to get me a maximum of this. Now everything's working out. We know this. We know that associated with area, right, is going to be this. We want to go MKS system of units. That's why we're using this as well. This is the MKS system of units. And then we got this. Okay. Now, we know various things, and we're going to use various things. We know that the E, in general, based on matters of what we've talked about, derivations that we have in other places, in notes that they have given to us, in information they have given to us, derivation that they have given to us, things that have been derived, that have been given to us in books and in notes that I've given to you folks that I've looked at in other places from brilliant people that have shown us how to do these things. I've tried to take their notes and try to make it somehow presentable. Hopefully it works out for you guys. But there's a lot of great notes out there. You don't need to get them from me. But we know from the mathematics that we do know, from the physics that we do know, that we've got the E is going to be NBA. Omega is the angular frequency. And this is the sine of omega t. Well, if you want to get a max here, the thing that's variable here is the sine function. It's the one that's constantly changing. The omega is not changing, nor is the A, nor is the B, nor is the N. Just the sine of omega t is changing. The maximum value it can have is the sine of pi over 2, equivalent to the sine of 90 degrees, which is 1. If this is 1, bam, you just got this part to the left of what I've circled here. And that's essentially what you're looking at here. That's where the Emax is going to be. The Emax is going to be N, B, A, omega. We know that F, that's an interesting point in its own right. We know that omega is 2 pi f. So we know that omega is 2 pi f. So omega divided by 2 pi is f. So we got this right here. We know that is, what is the frequency now? We're going to say it's this. For some reason, I just want to remember what they said here, guys. It's I haven't said a whole lot there, actually, guys. So I'm trying to figure out what they might be saying here. I don't know where the heck that's coming from. What is the frequency, huh? Well, yeah, I just said something here, which is actually true. Okay, well, I really just did put the carriage in front of the horse on this one. All right, guys, this is actually going to be the answer. You've seen it. Well, I hate to give away the end of the movie on this one, but tell you what I'm going to do. We know that omega is 2 pi f. We'll go from there. If I solve for omega, omega equals 2 pi f. F is going to equal omega over 2 pi. F is going to equal omega over 2 pi. So we got this. Tell you what I'm going to do. Let's stay with this. Very useful to us. And let's figure out where we want to go with this. We solve for omega. It's Emax over NBA, the product NBA. And so many ways to go here, guys. I mean, I can cut to the chase real quick, or if that's that, there's a lot of ways here, guys. Let me jump to it and see what happens. Omega is 2 pi f, so it's equal to all this that I got right here. This is slightly different than how I did it in the notes that are going to scroll for you, but that's okay too. That's all right. And let's see. All right, guys. Sorry, it takes a little while to erase some of these. Go here. You saw all the monkey business I did up here. I'm going to do it again. I'm going to divide by 2 pi on each side. F is going to be Emax over two pi That's it. If you plug in all the numbers, again now, and again, you'll see it when it's scrolling, guys. If you plug in the Emax that they gave us, I want to make sure, that stuff's easier done than said, but you got to look at what they're actually giving you. They told me Emax is 8.6 volts. A is 370 times 10 to the negative 4 square meters, and the B field is 0.025. It's 25 millitesla is 0.25. So, and this is 300. This is, big N is 300. B is 0.025. A is 370 times 10 to the negative 4. 2 is 2, pi is pi. This right here is 8.6. Grind out the numbers, guys, and you plug them in there for the actual problem. And that's all it's doing. That's all that's being done here. This is 4.93 hertz. .93 hertz, you guys, and that's going to be 4.93 hertz. They got 4.9 hertz. Good enough for me. It's the closest by far compared to all the other ones. 4.9 hertz. That's C. Again, the main thing, guys, to get us through any of this is acquire the data that we need to acquire. In this case, you're trying to find F. You know this, 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 you know that. Hey, it's not too much. Not too much to ask. I mean, they can get it. They can get it right. I'm running out of chalk, guys, like it's nobody's business, but that's all right, too. Some great chalk. It should show up pretty well on the board, you guys, I hope. All right, guys, that's 17. See what 18 says. For 18, they're saying, for number 18, the current in a coil with a self-inductance of 2.4 millihenries, which is what? Well, that's 2.4 times 10 to the negative 3 henries. 2.4 times 10 to the negative 3 henries. Again, you want to speak the units of the MKS system. When you got to do this, then you don't have to worry about the units when you're doing it. It'll spit out the units you want at the end, the right units, right? MKS system. The current in a coil with a self-inductance of 2.4 millihenries increases from 0 to 2.66 amps in a tenth of a second. What is the induced EMF in the coil? Pretty straightforward stuff, guys. Pretty straightforward. The self-inductance is L. E is given to us like this. If it's calc treatment, it's di dt. If it's non-calc treatment, we go to here. This can be done non-calc treatment. We got it to here. This right here, let's just get, I think they were talking about magnitude. Let me just, I'm almost sure of it. Right, well, what is the induced EMF? It's all right. Let's just go for a magnitude here, guys. It should be all right. So we got this. Okay, we got that happening. In terms of absolute value, we got L di dt. They're giving us positive numbers all over the place, so we should be all right. They're telling us 2.4 millihenries. That's 2.4 times 10 to the negative 3 henries. The current changes, goes all the way up to 2.66, starting at 0. And it does it in 1/10 of a second. That's it. It's the hardest part of the problem right there, guys. Right there, hardest part of the problem. It started at a certain point, got up to a certain point, or fell to a certain point. Here it got up. It started from 0, went to 2.66 amps in a tenth of a second. What is the induced EMF in the coil? That's all that they're doing, guys. So it's good to know this stuff. It's really good to know it. So what you have here is 0.06384 0.06384 volts. I guess let's make this thing 1,000 times bigger. If I make this number 1,000 times bigger, I got to make the volt unit 1,000 times smaller. That's a millivolt. That's 10. You know, make this 1,000 times bigger, then it's 10 to the negative 3. That's the millivolt we're talking about in that case. Let's see what language they were talking on that, guys. I always try to look at this and hopefully speak a little bit of their language. I don't know how I managed to mess that up, but that's a millivolt right there. Let's see what they're talking about. Right. Well, they got 64 millivolts for letter A. For letter A, they have letter A for the answer, which corresponds to 64 millivolts. That's close enough to 64 millivolts, you guys. Sure is. Again, you know you'll find that on the sheets when you're looking at it. The big thing is do the logic, get the answer, you guys. So that's 18. Let's get 24 and 25 and get an idea how we are for this first part. I'm trying to pace this over three films, you guys. So let's see 24 and 25 if I can do both. If not, we just do 24. We'll see how many there is. We'll take it from there. For number 24, number 24, they're doing some neat stuff here. For number 24, when a 47 microfarad capacitor is attached to an AC source, its capacitive reactance is 42.0 ohms. If instead a 150 microfarad capacitor, not the 47 microfarad capacitor that ended up having a capacitive reactance of 42 ohms, instead, not the 47 microfarad capacitor, but now put a 150. Instead, if a 150 microfarad capacitor is attached to the same source, what will be its capacitive reactance? Some little classic mathematics that goes on there, not excessively difficult, and very interesting as well. Let's take a look at it. Okay, guys. So let's see here. I mean, they're given two different scenarios here. A good comparison will get you to where you got to go. Let us see. Pretty simple ratios here. Basically, what we're talking about is one starting from the standpoint of, well, they're doing a lot of stuff here. I mean, they're saying when a 47 microfarad capacitor is attached to an AC source, we're assuming the source itself doesn't change. The omega of the current, and proportional to that, the F of the current, the frequency of the current, won't change. The omega won't change. And so that doesn't change, but one's a 47 microfarad capacitor, the other one's a 150 microfarad capacitor. So how do their capacitive reactances compare to one another when that's the case? So what will be the capacitive reactance for the 150 microfarad capacitor? We do know for the 47 microfarad capacitor that it's 42 ohms. So again, this stuff is probably a little more easier done than said, so let's just get to it rather than me delivering a speech every time. For 24, the capacitive reactance is 1 over omega c. And that's good. I mean, if you want to look at it that way, that's fine. It's the way to look at it, actually. Let's say that one of the capacitors we'll call C sub 1. One of the capacitors is C sub 1. So X C sub 1. So X C sub 1 is 1 over omega C1. X C sub 2 is 1 over omega C sub 2. Okay, sounds good to me. So this is really going to make it happen. I told you the omega won't change, presumably, because we're dealing with the same energy source. We're dealing with the same alternating current, alternating power source. The alternating current, we're dealing with that current that's there. That hasn't changed. The omega is not going to change. There's one of them's got C1, which is whatever it may be, whichever one you want to call what. One of them's 47 microfarads. The other one's 50 microfarads. The other one's 150 microfarads, and the other one's 47 microfarads. So you're looking at this right here. This stuff's just a lot easier done than said. Let's find out what the capacitive reactance is going to be when for the one capacitor associated with a higher capacitance. So if there's a high capacitance, probably a lot easier for the current to get on and off it. So it's probably going to be, its reactance is not going to be as big as it was earlier, where the other one had something like 42, as we said, right? Tell you what I'm going to do. Let's call X sub C the second one under consideration. So we'll call it X sub C2. We'll divide, look at these two things right here. let's take the bottom one and divide it by the top. Let's take the bottom one and divide it by the top. And what we end up getting is well, okay. Again, it's easier done than said, and sometimes writing this stuff down. When you're doing this, you got to do it as efficiently as you can. Some stuff you can skip the steps on if you're comfortable with what you're doing. This divided by that is this multiplied by the reciprocal of that. So this bottom thing flips over. You multiply, the omegas cancel, and you just got this. This flips, you multiply, the omegas cancel, you got this right here. So we got this. Guys, that's probably the hardest part of the whole problem, to be honest with you. We're going to find what the capacitive reactance is of the top one, xc sub 2. We're going to do that by multiplying by xc sub 1 on each side times C1 over C2. xc sub 2, we found this one to be 42, they told us, the one associated with the 47. This C1 was the one associated with the 47. The C2 is 150. These are microfarads, right? Just make sure here, guys, we got speaking the same language here. Yeah, 47 microfarads and 150 microfarads. Got to watch out. You got to watch out. If this guy is giving you an answer, if this is giving you an answer at the end of the day of 42, if you got 42 out of this one, however you got it, we can actually find the omega that would give us that. Nobody's asking us to do that, but we could solve that. You know, if I already know what the capacitance is, and I don't know what omega is, I do know what 1 is, I do know what C sub 1 is, don't know omega, but I know this guy, I can just solve for omega. And then from there I can get the F, and it's going to be the same F for the other one. Okay? Well, yeah, that's all well and good. Yeah, it's not really the hard part of this. It's a neat problem in its own right. But I want to know, this thing right here, they told us, when this guy had a capacitance of 47 microfarads associated with a particular omega for a particular alternating circuit, and we're not changing the circuit for either scenario, so it's the same omega for both, as we said. If this C sub 1 is given whatever it is, and we said it was 47 microfarads for C sub 1, there is an omega. 1 divided by the product of some omega times 47 microfarads got me 42 ohms. This one, it's the same omega, don't know what it is yet, but this capacitance, this 1 is 1, this capacitance is 150 microfarads. I guess I can cancel the omegas out, get them out of our life, guys. These C1 and C2 we already know. This one we know, but this one we don't know. Hey, we only got one unknown here, and if we do a ratio, if we divide the bottom equation by the top equation, we got what we got there, or we got what we got here, the omega. Now, you can come back and, hey, by the way, what was the frequency of this thing? You could solve for the omega. You can plug in all the values that you know. You don't have omega, you solve for omega. It's going to be the same in both cases. So you play this, guys, and, okay, that was 24, as we said, right? So we got that. At the end of the day, the larger capacitance capacitor, more than 3 times the capacitance, has less than 3 times. The larger capacitance capacitor got you this amount of capacitive reactance compared to the 42 ohms earlier. You've got less than 1/3 the capacitive reactance when the capacitor in question is more than 3 times what the other one is. Pretty interesting. Makes sense. It can easily get charge onto it. So there's not really a resistive aspect to it as much as it was earlier. Something to kind of think about. At the end of the day, we got to get the problems right too, right? I mean, we got to know what we're doing, get the problems right. So you're looking at this for number 24. 24, they're saying 13 ohms. D. Letter D, 13 ohms. Right, 13 ohms. How much is that? Well, yeah, it's about 13 ohms. Good enough for me. Okay, that was 24. Let's look at 25. So for 25, they're saying, for 25, a 400 ohm resistor and a capacitor are connected in parallel across a 300 hertz source. Hertz describes F. If you go 2 pi times F, you get omega. This is not omega. The 300 hertz is F, the frequency. A 400 ohm, once again, a 400 ohm resistor and a capacitor are connected in parallel across a 300 hertz source. If the amplitude of the current in the resistor is equal to that in the capacitor, if the amplitude of the current in the resistor is equal to that in the capacitor, what is the value of the capacitance? That's neat. Talking about it, you're going to play the game like this. And we've got some of the everything that we need here and everything. So we got Imax. Imax are the Imax going, the amplitude. Amplitude means the maximum. The amplitude of the current is a fancy way of saying the Imax. The amplitude of the current is a fancy way of saying the maximum value of current. The maximum value of current in the resistor is the same as the maximum value of current that would go through the capacitor. So these are equal. Well, that means that's going to happen at a particular Vmax whenever it does happen. Vmax divided by R, V divided by R is current. Vmax divided by R is current. And Vmax divided by X sub C is going to be current. Makes sense to me. Whatever the Vmax is, Vmax equals Vmax. Divide by Vmax on each side, you got this. The hardest part of the whole thing right there, guys, basically. 1 over R equals 1 over XC. What does that mean? Well, if two quantities are equal to one another and they're not zero, we're assuming neither one is zero, if two non-zero quantities are equal to each other, their reciprocals are equal to each other. If these two entities are equal to each other, their reciprocals are equal to each other. It's the only way it's going to work. X sub C is 1 over omega C. Well, here we go again. Let's get the reciprocal of each side because we're shooting for the capacitance. So we got to solve for C. We can do this a bunch of ways. If two things are equal, their reciprocals are equal. We've heard that before. We got this. Solve for C. Divide by omega on each side. See, omega is 2 pi f. That's the omega. Here's the r. Let's go. C is 1 over, let's see how we can write this a bunch of ways here. I wrote it a little differently, but it's 2 pi times 300. They told us 300 is F. Times R problems long enough, sometimes you can't remember what the parameters are that were given to you or what the values are. They're saying, yeah, it's a 400 ohm resistor. Well, there's a lot here. I mean, we got 1.3. We got 1.326. 1.3263. 1.3263 times 10 to the negative 6 farads. Well, we've seen the 10 to the negative 6 enough times to know what we're talking about. This is 1.3263 microfarads. You can see a lot of times they're going to give it. They might not. They might have left it as exponential notation. I haven't looked at the answers lately, guys, so let's look at it while we're doing this. What they're doing is they got right, okay. I got 1.3263 microfarads. That rounds to 1.33 microfarads, and they got 1.33 microfarads. That's A. Okay. All right, looking pretty good. It's 25. Let's see how many I count here, guys. I'm looking to do 36 of these, so maybe 12, roughly 10 to 12 every time I make a film. That would be 2, 4, 6, 9, 11, 13, 15. So there's 15 of them right there, guys. Yeah, about 15 of them right there. Let's do, possibly not do. We got enough under our belt, but let's do it anyway. Let's do 31 really quickly. It should go pretty smoothly. Okay, guys, let's knock out 31 really quickly, and that'll be it. And then we'll go to part 2. We'll go to film 2 afterwards. But since we started at this point, let's stay with it. Let's do something about it. All right, guys. For 31, you guys, a transformer consists of a 780-turn primary coil and a 1,403-turn secondary coil. So once again, for problem number 31, we have a transformer that consists of a 780-turn. A transformer consists of a 780-turn primary coil and a 1,403-turn secondary coil. If the current in the secondary coil is 3.49 amps, what is the primary current? Pretty straightforward. Should be okay for us. Again, the possibility of so many questions, folks, I don't want to make this stuff impossible. I want to make the answers pretty short, but at the same time challenge people a bit, but also make it reasonable, because the answers can be rather short to get it here. If you want to talk about, regarding the transformer, compare the potential differences. a big potential difference is indicative of many turns. Big potential difference, many turns. Small potential difference, small amount of turns. There's a lot can be said here, guys, to get this under control. So we can say the more turns that there are, so let's see exactly how you want to do this. The more turns that you are, the power output is going to be identical. The more turns you have, the greater the voltage, but the less the current. If you triple the number of turns, it's associated with 3 times the voltage, but 1/3 the amount of current. If you multiply I times delta V, it should come out the same in either instance. So let me kind of cut to the chase on this, for better or worse. I delta V equals I2. Forgive me. I1 delta V1. I1 delta V1 equals I2 delta V2. If this is really big, that's small. If this is really small, that's big, but the product comes out that way. And that's where this is coming from, vis-a-vis this. If there's a lot of turns, you're not going to have as much current, but you're going to have proportionally more voltage. If there's not as many turns, you're not going to have the voltage, but there's going to be more current. So the I delta V, I1 delta V1 equals I2 delta V2 is kind of a good way to look at it. Make a long story short, I'm kind of jumping around here a little bit, and we've seen this in the notes, we've seen this in various books, in our own book as well. To one degree or another, we should have seen this in our own book as well, but we've seen this in numerous places. As we said, do that kind of ratio, and it's the same as the N2 over N1, but I'll tell you what, let me put in the middle of all this, it is indicative of real big voltage means big current, and the big current is the other way around. Real big voltage, small current, real small voltage, big current. So it's kind of odd how it works out, but it works out that way. It kind of makes sense. The way you want to look at it is maybe you look at the hose being really long. I guess it's going to be hard for a lot of water to get through it. You can maybe look at it like that as an intuitive look at it. So when you look at all this, you can play a whole bunch of things here. I1 over I2 equal, they gave us this. They didn't tell us too much about, they didn't tell us anything about a potential difference. So we had to kind of, we got to infer what we could infer, folks, vis-a-vis the turns. And it did tell us something about the current. The secondary, if the current in the secondary is this, it's probably going to be a lot more in the primary because the primary is about half as much. So it's probably going to be double what that is, probably on the order of 7, 6 point something, 7, whatever. We got up to here. Multiplied by I1, there's a lot of ways to go here. Multiplied by I2 on each side. I2, we'll say, is, again, the way, you got to know what you're calling what, just be consistent. What is the current in the primary? What is the primary current? The primary current we're going to call I1. If I1 is the primary current and 3.49 is the secondary current, and the secondary's got 1403 turns, and this one's got whatever it's got. I mean, so they're saying here, let me look at it. Yeah, there's 780 turns in the primary and 1403 turns in the secondary. If the current in the secondary is 3.49, what's that? So the current in the secondary is 3.49. I don't know what that is, but the secondary one has 1403. The primary one's got 780. Hey, it's just simple mathematics at that point. Just do the ratios and find what it's doing. Again, you don't need to run across a whole blackboard doing an exam. You just sit here and you do it as you know how to do it. You figure out how you're going to put this. So they're telling us, they're basically telling us the whole thing. This is 3.49 amps. I don't think they're putting milli or micro or whatever here. I don't think. They are not. It's just 3.49 amps. And the secondary's got this. The primary's got this. and the rest is mathematics, and we said somewhere in the ballpark of 7, 6 point something. Well, 6 point something is a better estimate. I sub 1 is 6.2775 amps. 6.2775 amps. And there it is. We figured that the primary having less turns, almost half as many turns, is probably going to have double the current or close to it. Somewhere in that neighborhood. 6.2775 amps. 6.2775 amps. I got 6.28 amps here. 6.28 amps. 6.2775 amps, 6.28 amps. Sounds about right to me. And that's C. Again, the procedure is everything. People are going to switch letters around all over the place. I mean, it's not, oh, gee, I'll remember these letters. These letters mean nothing. All these letters get changed. You've got to know how to do it. Get the right answer. Get the right answer. And that's number 31. All right, guys. I think I think we could go more right now for part 1. Let's not. Let's stop it right here. And let's go to part 2 and then part 3 and be done with it to get all 36 problems. All 72 problems are going to scroll at the end of each one of these 3 videos. The exam problems, how they look, the practice exam problems, how they look, all 72 of them are going to scroll, and all the solutions to all 72 of those problems in relatively good detail. Those are also going to scroll at the end of each one of these parts 1, 2, and 3, at the end of each one of these films. Okay, guys. Thank you for your time. We'll get to part 2 the next time we're together. Take care. Bye now.